Hi, Swami. Good afternoon, Bhageshri and Kaushik. Can we get started?
Good evening, Malo. Yes.
Yeah, let's start. Okay. So thank you to the two participants for joining today's session. Let me just share my screen and get started. Okay. So I hope my screen is visible. Yes, no.
Hey, can the participants confirm whether Malo voice is clear or not? I'm getting some disturbance.
It's feebler than usual.
Okay. Yeah.
All right. One second. Let me just.
It could be because of your headphone, Malolan.
Yeah. One second. Let me do it. Is it better now?
Slightly better. There is a lot of bass.
Yes. Okay. Yeah, I don't have. Okay, is it better now?
Slightly better, but it is manageable.
Okay, I do not have. I do not have another mic, so yeah. In my audio test, it says it's fine, so I do not know why this is happening. All right, let's get started. All right, so in this guys session, what I wanted to do was there's been a request in the discourse to discuss the assignment. So I'm going to discuss not the solution, but the thought process of how you tackle this problem and how one question helps you in identifying what method you can use. There will be 2-3 methods that you can use, and how do you identify what you have to use. So that is what I'll be discussing in today's live session, the first half. The second half, what I want to do is I want to talk to you about week 7 content. I hope it is already launched. So in week 7, there is one particular topic called recall, precision, and accuracy, right? So I want to give you a method by which you can easily identify based on the problem how to answer these questions of recall, precision, and accuracy. All right. So that will be the focus of today's discussion. With that being said, let's jump into it. I hope all of you have solved the assignment and submitted it and got some mark. So I will just talk to you about the procedure for solving it. So before we start, what was the data that was given to you? How was it distributed? Was it normal? Was it Poisson, exponential, uniform? Any idea? If you had solved it, you should have got to know by now.
We are talking about assignment 1, right?
Assignment 1.
Okay, that was normally distributed.
That was normally distributed. Fantastic. So whenever you want to, so the assignment 1 was basically about fitting a distribution. Okay. So whenever you want to fit a distribution, the first question that you should ask is the step 1, which is what is my data? And here I'm not talking about the problem statement data. I'm just telling you what is given to you. And there could be 2 things that could be given to you. The first one could be just a table, right? Or a list of values. This is what was given to you, list of values. A second way of giving you a data is the frequency table. So the frequency table is basically a refined version of this. So a list of values or a table containing the values for a random variable will be converted into a frequency table, and then the goodness of fit test would be done. So in your basic statistics course, You would have done these tests of independence, goodness of fit test, so on and so forth, on data that is already given to you in a frequency table. Here, in a business analytics course, the business problem would give you a list of values. From that, you will have to generate the data. So that is what this is all about. So in our assignment, we have been solving this particular type of a data that is given to you. So what is my data? My data for the assignment is a list of values that were given. And this list of values, the business problem is the thickness of coat, the paint thickness that was that has been applied to different cars that was produced on the line. So that is the first thing that you should understand. So we are given a list of tables. So ultimately, to perform a goodness of test, you have to create the frequency table. And that was the entire assignment all about. Okay. Now, given a list of values, right? The second step is to identify possible distributions that you can check for it. You have n number of distributions out there. You can't go around and explore everything. So you'll have to narrow this down. So that was basically your first question, right? To fit a histogram. So when you fit a histogram, you can basically identify whether the distribution is symmetric or non-symmetric, right? And from the histogram that you got for the assignment, what did you identify?
Just looking symmetric.
It was looking symmetric. So in a symmetric distribution, there are several, right? Uniform and normal are two symmetric distributions that are very common. From that, we want to further narrow down and identify what could be the possible symmetric distributions, which is step 3. There you will get the descriptive statistics. This would include the mean, the 50% quantile, the skewness, so on and so forth, right? So all of these can be got to narrow down on what kind of symmetric distribution this is, right? And those would be your third question. What were your different kind of descriptive statistics? The mean, the 75% quantile, 25% quantile, the standard deviation, the variance, so on and so forth. So that is what we wanted you to do. So once you have done these 2 steps, you will be able to narrow down and say, okay, this seems to be a normal distribution for me. Okay, till that is your step 3. Let me just do one more thing. So that was that. After this came the question on using this and choosing the hypothesis. What could be your underlying assumption about the distribution? So here I had actually given you several options, and these were the options that were given to you, right? So data is distributed normally. The data is distributed normally with a mean of 20. Data is distribution as a Poisson with mean 20, uniform with mean of this range, right? Now from this, can you tell me, I've already told you it's a normal, so we'll leave out all of these. Between these 2 statements, why is this statement the right answer? You have already been given the answer. I want you to tell me why that statement is the right answer.
The mean is around 19.
Okay, 90 approximately 20. Why I've given you 20 is because the question says
20, yeah.
20, right? So there is a lot of things saying that it was around the start. Mean of the data was 19, but Swami was thinking it was 20. So the distribution with a mean of 20 should also make sense, right? But it is wrong. Why is that?
The thought process I had was we are trying to ascertain whether it is 20 mean or not. We do not know yet until we do some analysis on the data.
Okay, what do you mean by that? That is almost right, but what do you mean by you're trying to ascertain that whether it's 20 or not? Is that what you're trying to do?
See, we are trying to get some parameters from the data. I mean,
Okay.
get some statistics, sample statistics from the data.
Okay.
And we want to know whether whatever we are getting are significant or not. In the sense, like we want to do some testing and figure out whether we are there or not. Until then, we do not know whether it is 20 or.
All that is fine. Whether it's 20 or not is fine. But what are you testing for in this? What is your goodness of fit test doing? That is the core reason why this statement is right and this statement is not.
So the hypothesis is that it is 20.
Hypothesis is that it's 20, then this statement should be correct, no? With a mean of 20 is correct, no?
Oh, sorry, maybe the other one, I think.
Again,
We are trying to find an evidence that it is 20. So hypothesis is that it is just normally distributed without any mean.
are you trying to find evidence that it's 20? Really?
Yeah, because the problem that you stated is like we are trying to put a paint and we want to make sure that paint is average 20, right?
It says he's worried that it is overcoating.
It's worried that it's overcoating, that is okay.
Which means it's greater than 20.
It could be greater than 20, okay. But
That's the hypothesis.
What is the test that you are doing?
Goodness
Why
of
am
fit.
I? Yeah, so goodness of fit is for what? Why I'm emphasizing on this point is a lot of you have got confused between goodness of fit test and something else. Goodness of fit test is only checking. Okay, I'll give you the answer. So the goodness of fit test is only checking whether the data is coming from this type of distribution or not. It is not checking whether the data is coming from a distribution whose mean is this. That you will do a check using testing of hypothesis on the mean, right? So you will now, after doing goodness of fit test, you will say, okay, the population is normally distributed, fine. Then you will go on to do a test of hypothesis on the mean to check whether this population, this is coming from a population whose mean is 20 or greater than 20, right? So in your statistics course, you would have been taught different types of tests, hypothesis test. One is test on the mean, and the other is called goodness of fit test. And then you have the test of independence. So the test on the mean will tell you whether this sample is coming from a population whose mean is so much. But a goodness of fit test will only tell you whether the sample is coming from such a distribution or not. You understand the clear difference? Is that clear?
Yes, sir. Clearer.
All right. So that is why this statement is not true. This statement, the data is distributed normally with a mean of 20, can be made if you are doing a test of hypothesis after doing a goodness of fit test. Let's say you are not doing a goodness of fit test. Then how will you change this statement? You have not done a goodness of fit test, so you do not know the distribution. You have a sample, you just want to check the mean. Then what would be your statement look like?
The data has a mean of 20 millimeters.
Data is coming from a population whose mean is 20. That is all. Right? So that is where this particular question does it. So once you have got all of this, you will have to make the null hypothesis, H naught. And the null hypothesis will state that the data is from a particular distribution. That is all it will state. It will not tell you the parameters of the distribution. If you are going to do a test on the parameters of the distribution, that is test of parameters, right? Whether it's the mean, the standard deviation, whatever. That would be a different test. This is only a goodness of fit test.
I have a question, sir.
Yeah.
In the lecture, when we were figuring out whether it is a symmetric distribution or unsymmetric distribution, while we were taking some parameters, we checked mean and standard deviation. Because both are close to each other, then we said it is Poisson. And also we said kurtosis is negative, so it cannot be normal symmetric distribution. But here for the data, kurtosis is coming as negative. Is that should we ignore that?
You'll have to see everything. Now, this is a sample, one small sample you have got, and from that sample you have to see everything else. Sometimes you might have got a sample towards one end. That could be a reason.
So, what is the tipping point? What is the what is the strong evidence which actually helps us to decide that it is a symmetric distribution?
You see it along with your histogram. You see it along with your histogram. The histogram and this thing and your distribution, and though your kurtosis might be negative, what you will actually see is how is spread across the 50th quantile, 25th quantile, 75th quantile. Is your 50th quantile matching your mean? Then it predominantly means that the mean and the median are the same, which means it's spread evenly on both sides, right? So it's more subjective. That is what I'm trying to say. These two steps will not give you concrete evidence against this is the distribution, this is not the distribution. It will only help you narrow down. So if you have a doubt, you have to go for a check where everything is checked about. Making sense? This is only yeah.
Sorry, I wanted to add another point here. So that discussion on having negative values, so that was said in the context of a Poisson distribution. For example, when you say this data is Poisson distributed, you cannot have negative values. For example, you cannot say -2 people are entering the classroom. So these kind of things are not acceptable. So therefore, we said that in the histogram, if you have negative values, it cannot be a Poisson distribution. That was the context, and I think that was misunderstood here. I just wanted to clear that point. Over to you, Malo. Please continue.
Yeah. I hope I've answered the question. So even if you get some negative values regarding symmetricity, is what I'm trying to say, it could be because of the data. So you'll have these two steps of histogram and this thing will only help you narrow down to a certain extent. It will not give you a concrete evidence, okay, this is normal, this is uniform. Even at this point, what I will usually do is, though it's symmetric and these numbers have come, I would have checked for both uniform and normal, then answer this question.
Okay.
Making sense? Got it? So these are and this is precisely the reason why you have a statistical test called goodness of fit test, because that gives you statistical evidence for this particular kind of a unclarity that you have from the descriptive statistics. Okay. Right. So this is step 4. So this is very important. The hypothesis for the goodness of fit test is only that it is coming from a particular distribution or not. It will not check whether that parent distribution has that mean or not. Okay. So that is step 4. Then comes step 5.
Sir, I have a basic question. Can I ask?
Yeah, go ahead.
Yeah, there was skewness in this distribution. So why it is normal?
It can have, no? Skewness is only telling you which side is being pulled. This could be pulled to. Skewness is only telling you which side it's going to be pulled. It need a normal distribution can be right skewed, left skewed, right? There can be skewness in a normal distribution.
There can be.
Okay. There can be, of course.
Okay. Okay.
You have a right skewed normal distribution, left skewed normal distribution. How do you say that? Which means the tail is more on the right side, the tail is more on the left side, no?
Okay.
Yeah. So you do have skewness. Skewness can occur, and like I said, it will come, and this is only a sample. So you would have taken a sample where more points would have come from one side of the distribution, parent distribution. Okay. Yes.
And negative skew just means left tail, is it? Negative skew?
No, negative skew means left tail, yeah.
Left tail.
Lower than V. Negative skew, I think, means right tail. Let me just get back to you on that. Just put it in discourse. Negative skew should be in right tail because it is more towards the right. Swami, is that right? Negative is right tail, no?
Yes, I think the second thing was yes, is right.
Yeah, negative is right tail because the values are more away from the mean, more on the positive side of the mean, higher than the mean.
Okay.
Negative skew is right tail. Yeah. Okay. So this is step 4. I hope everyone is clear up to this point. Let me move on to step 5. Step 5 is where the table, or let me not confuse, let me say a list of values. So that might be more clear. So the list is now converted to a frequency table. This is where the process of cleaning the data happens. And here is where you have two ways by which this frequency table can be generated. And this is deliberately why we said equal size. So equal size could mean length or area. Both means equal size. What I mean by area is probability area. Right? So both, if your interval length is the same, that could also mean equal size. If the probability area under the curve remains the same, that is also equal size. How do you identify which to use for this particular assignment? For that, you need to go and check this particular question, right? So now a chi-squared goodness of fit text is carried out such that the data is grouped into 6 bins of equal size. So you have two options. Then answer the following question. And your first question is, what is the expected frequency in each bin? So this question basically points to the fact that each bin should have the same expected frequency. And if it's a normal distribution, it can only mean one thing, that the probability area is the same. All right. So that is what you should have done. This is what you should do. So when you are creating a frequency table, what I mean by, in fact, let me go one step further. What I mean by length, basically, let's say I am putting for our own distribution. I believe the values were between 0 to 25, I guess. Yeah, 0 to 27. Let me put it as 27. It should be around 25, slightly less than 25. Let me just say 27. I could have split it in equal length. Would have been, okay, let me put 25. Let's say split it by 5 for points, for just for convenience. 0 to 5, 5 to 10, 10 to 15, 15 to 20, and 20 to 25 mm thickness. This would have meant equal length, right? But the observed frequency and the expected frequency would be different. This could have some value of 7, this could have some value of 10, this could have something else, this could have something else, this could have something else. But your question number 11 says that all of these is the same, which means this is not right. You should have observations which are of different length, but the area under the curve, this area would be the same. So the number of observations here would be the same, which is 8, right? So I want you to split it into 6 bins. So you have, how much do you have? 6 bins each of 8, right? Yeah. So you had 48 observations. I want you to split it into 6 bins. Each bin will have 8 observations. So accordingly, you should create the interval length. That is what it means. Okay. I spoke to you about equal length during our live session, and probability area was what the code was given to you. Okay, everyone with me so far? This step, did you guys understand? This is where a lot of people made a mistake. With me so far? Yes, no?
So
Yes.
the length here, when you go with length, that is the number of observations. So that's equal number of observations.
That is this number, thickness of paint in this case. What is the coating of thickness of paint? Is it between 0 to 5 mm?
Okay.
And then I will say how many cars were there. That is the observation.
Okay. Whereas now we are splitting by the number of observations.
Now I am splitting by the area. I am expecting that 8 cars should fall under each of my bucket. So what should be the length accordingly?
Okay, how does 8 automatically transfer? But I mean, how does it automatically mean probability area?
Because I am asking you for what is the expected frequency in each bin. I want each bin to have the same expected frequency, and you have been told to create 6 bins, and there are 48 observations. So 48 by 6 means 8. So every bin should have 8 observations, and to have 8 observations, what is my length is what I'm asking you. And for your case, it will basically be between these ranges, minus infinity to, since it's a continuous distribution, I'm putting minus infinity. You can also consider 0, whatever. To 13.7, since I've given you 5 decimals in the question, I'm giving you 5 decimals here. 13.78959. This would be my first interval. My second interval would be 13.78959 to 16.68398. Yeah. Then this would be 16.68398 to 19.00688. Yeah, so this is how it will come. So if you take this interval, the length between these two, the thickness of paint, the length is going to be 2.8944, and this is going to be a length of 2.3229. Let me just check that once more. 16.68 minus 13.78. Yeah, 2.8944, correct, approximately. And this length would be 2.33. So the length is different, but if you go and check, I also have that in my. Yeah, so this was your original data. So bin 1 is between 0 to 13.78. These would be the observations that is there. So there will be a total of 9 observations in your sample, whereas in your population you will expect, so your observed frequency would be 9. In your, if it's nominal distribution, the population would be having 8, which is your expected frequency. So the expected frequency would be 8. Similarly, for this length, the expected frequency is going to be the same. It is going to be 8. The actual frequency would be, what is in bin 2? We will have 5. Right? So this is how it goes. And another question that most people asked in this particular assignment is, how do I know what is bin 1? Basically, convention says you will go in the ascending order, right? So minus infinity to 13, 13 to 16, 16 to 19, so on and so forth. So that is why bin 1, bin 2, bin 3, bin 4 are. So that was this particular question, this particular series of questions.
So, sir, how do we get those values? 13.78.
This one. Just go to our code. We have actually given it to you in our code. If you generate it, it will automatically give you these values. That's a line in it.
Oh, you mean in the solution, is it?
In the code that we have provided to you, the demos that we have done, the live tutorials, and the code that was given, the data 3, third set of code for which there is no video tutorial, that code also has this particular line which will generate these intervals for you. It will tell you 13.68, 16.9, 19 point something, and so on and so forth. Right? All of that will be generated and printed. Let me just check whether it is here with me. Just give me a minute. Open it up. I should not open your next assignment. So this line of code that was given to you in your file that you have in your drives, this will generate the intervals based on the n, the sample mean, and the sample standard deviation. Okay.
So it's essentially doing, it's creating 6 equal areas of that normal curve with that mean, is it? That's all it's doing.
That is all it's doing. That is
mean
all
and standard deviation. Okay.
Exactly. That is all it's doing. It's just telling you these widths. And after this, we would have given you the observed frequency and expected frequency, and observed frequency. These we have basically done manually and given it to you. You can write piece of code for that also, but we are not looking at it. So if you basically go to the data set and say 0 to 13.7895 less than or equal to that value, you will get 9 values. Then between this value and less than or equal to less than this value, you will get 5. Between this value and less than this value, you will get 9. That is your observed frequency, which is the answer to your question. Okay.
Yes, sir.
Everyone clear? This was with respect to the doubts that a lot of people had. What is meant by equal length, equal size? When we say equal size and we say all the expected frequency should be same in each bin, what is it? That is basically an indicator to show you this. We have not directly said equals create intervals of equal area. We didn't want to make it so very easy. So we said equal size and gave you this question as a hint for it. Okay. So once you do that, you will be able to get the frequency table, basically with those values 888. For your case, it would be 6 bins. Let me just put bin 1, 2, 3, 4, 5, 6, and they are observed frequency and the expected frequency. So it will all be 8. This will be 8, and these will be a different values 9, 5, something. There was a 110 here. Yeah, those will be the values that you will have. Once you have got this expected frequency table, then after this, step 1, which I said 2 scenarios, both merge together, and you can proceed. All right. So the next step, step 6, is simple. You just have to calculate the chi-square. SQARE, which is summation over I is equal to 1 to 6 number of bins observed minus expected, the whole squared by expected. Yeah, that will be a value, and for your case, we'll get it as 2. Right? And the degrees of freedom is nothing but k, which is your number of bins, minus p, number of parameters, minus 1, which is going to be k is 6 minus 2 minus 1, because we are estimating the mean and the standard deviation. So there are 2. So that will be 3 degrees of freedom. So you can compute the test statistic for chi-squared 0.95, 3 degrees of freedom, you will get something. And if this is greater than this value, this will be 7 point something. If it's greater than your chi-squared test statistic, you will do what?
Accept.
You should not say accept. You should always use do not reject. It's always whether you reject the null hypothesis or do not reject the null hypothesis.
Okay.
Yeah. So do not reject the null hypothesis. All right. Everything after this should be clear. One small clarification is that in our code, what we did was we did have it here. All right. In your code, okay, not my cursor. I don't see this. Okay. you have observed expected frequency. Then we have not written anything. I will update this and put it in the drive. It should have actually been delta degrees of freedom. That's a discourse post on this. It should be k minus p minus 1. The value should be put here. This particular term we missed in our code to put it. So we have given you marks if you have just done OBS exception, the code formula. This we have not added it. So whether you have given an answer with this or with this, the p value, we have given you marks. Okay, for assignment for this particular assignment. This is basically where your degrees of freedom that you compute comes into the code. This we have missed it. I will make sure that it is updated and available by the end of this term. Okay. So this was with respect to assignment 1. Any doubts, any queries? You got the thought process of how you tackle this particular assignment?
Just one question. So the degree of freedom, is it because it is continuous and we are binning it? The bins, the k is actually 6, or would it be 48 otherwise?
No. That is n. No. So n is where n is sample size. K is bins. In a chi-square test of independent, chi-square goodness of fit test. What are you doing? You're basically splitting the distribution into some pieces, any number of pieces, k number of pieces, and in each piece you're telling you have observed so much and you're expecting so much. Is this difference significant? Is what your test is checking, right? So in each piece, if that difference is significant across all pieces, then it will say that your assumed distribution is not right. So that is why it is always k, number of bins.
Right.
Got it? So
and I was just comparing this to the linear regression where we take the number of
that is number of points based on the whole point you are fitting now. All the points affect your affect your beta naught, beta 1, so on and so forth. So there you need n. Here you are splitting the entire distribution into bits, and in that bit you are checking the observed expected and whether this difference between the two, O minus E the whole squared by E, this proportional difference across the different things is significant, is what your chi-square is checking.
Right.
That is the reason. Okay. Yeah.
Got it, sir. Thank you.
All right. Anything else? Okay. So this is with respect to your assignment 1. The thought process in a nutshell is first do some descriptive statistics, histograms, and first do some visualizations and descriptive statistics, histograms, and the means, median, mode, the different parameters for the sample, and narrow down on possible distributions. Then based on the narrowing down, you then do a chi-square goodness of fit test to see whether the assumed distribution is matching the sample, whether the sample is matching the assumed distribution. And all these computations are done under the assumption that the null hypothesis is true. So if my population is coming from a normal, then my expected frequencies are this, and the observed frequencies are this. If this difference is not significantly high, then I would say my null is I do not reject my null, and hence my population is whatever I have assumed. If not, I say that the sample is significantly different from my expected values. Hence, my assumption that it is the parent distribution is something can be rejected, right? So that is the entire process in a nutshell. Okay. So this was your assignment 1. Any questions apart from this in assignment 1? No questions. Okay. Then let's go to logistic regression. Have you all seen week 7 content?
I have only seen in bits and pieces, but there is some logistic regression covered in machine learning techniques also. So I don't know if it's related.
Okay, I'm just going to talk to you about a technique to not get confused between recall, precision, and accuracy. So I need to know whether you have heard of these terms somewhere else. Because
MLT
Yes,
we
we
have heard, yeah.
you have heard, okay. And have you heard
Yeah.
about a confusion matrix?
Yes.
yes.
All that is clear? Fantastic. Okay. So what is a confusion matrix?
So
It's a table.
It's a table between like what we guess whether it is a true positive or true negative.
Fantastic. So what are the rows values and what are the column values?
So it's
Predicted labels and actual labels.
Correct. So what comes in the rows?
There is a confusion. Some literature is puts actual on the as rows, and some places I saw actual as columns.
Very true. So there is this thing. Usually this is the convention: actual 0, 1 and
predicted. Yeah.
predicted 0, 1. This is the most common convention. You can find it in other ways around as well. Okay, so but this is the convention that we'll follow because it is predominantly accepted. Number one. Number two, your tool output, Python output will also be in this form. The confusion matrix that you get from Python is also actuals on the rows, predicted on the columns, and it's always 0, 1, 0, 1. Okay, right. Now the important thing to note is that we have two labels. We have a 0 label and we have a 1 label. So based on our focus, the recall and precision values will change. Okay, let me start off with the most intuitive one. Let's say we want to predict once, right? We are interested in whether the event has happened or not. Whether the event has happened, not whether the event has happened. The happened means 1. So interest is to predict 1. That is what you have built your model for. Then what is a true positive? All right. So a true positive is whenever the actual is 1 and the predicted is 1. So that is the true positive. Okay. I will first write the table. Then I will tell you how you can generate this table for any case, a simple trick to remember it so that you can generate it for any case. That's basically a cheat code, let's say, so that in interviews, tomorrow in your exams, you don't have to remember what is it for this scenario, what is it for that scenario. I will help you, I will give you a trick to remember it towards the end. So that is a true positive. When you want to predict 1 is what you want to predict. 1 is what you have actually predicted. So that is a true positive. Then a true negative is 0, something that you do not want to predict, but 0 is in the actual, and that 0 you have correctly predicted, that is a true negative. Okay. Then comes the question of when your actual is 1 and the predicted is 0, what is this? This value, what is it called?
False
It is
negative.
a
False
false negative. Okay, right. So I have falsely predicted a 0 when it is a 1. Actual is 1. Then I have falsely predicted a 1 when it actually is a negative. So that is a false positive. So this is the table when you are interested is to predict 1. Okay. Now, what is accuracy?
Total truths divided by total.
Total number of correct predictions. The proportion
Yes.
of total number of correct predictions.
Yeah, ratio.
So the total number of correct predictions is true positive plus true negative divided by all my predictions. Among all my predictions, how many are right? So true positives plus true negatives plus false positives plus false negatives, which is basically my sample size. So that is accuracy. What is recall?
True positive divided by TP plus FN.
TP plus,
FN.
what does that mean?
Among positives, how much have I correctly predicted?
Are you sure?
Confusion starts here.
No. Confusion starts here. It's not FN.
It is FN, sir. Correct.
Recall, right? Or row. Yeah, correct.
So among the positives,
Yeah,
how much
correct.
have we really correctly predicted?
Correct. So amongst the variable of interest, please note that amongst the variable of interest, which is 1 that I want to predict, how many have I correctly predicted? So that is a recall. Okay, just give me 1 second. I'll close this. Okay, I don't believe this is right. Are you telling my cheat code is wrong?
Malalan, it's correct, Malalan.
Yeah. Okay, I'm just checking. Recall is right. Yeah, correct. Okay, for a second I was looking. Okay, right. R is rules row. True positives by true positives plus false negatives. Yeah. So amongst, when I'm interested in predicting ones, how many of my actual predictions are ones as compared to all the actual ones? That is my recall. Then what is my precision?
True positive by true positive plus false positives.
True positives by true positives plus false positives. What does this tell me?
Out of the positive detected, how many are true? Like, what is the ratio between actual positives, total positives?
How amongst all my 1 predictions, how many proportion of that is right? So the precision tells me with respect to my predicting ability for my target variable, which is 1. And the recall tells me about my ability to predict ones amongst all the given ones. So that is the difference. All right. One takes the columns, the other takes the rows. Okay. Now comes the interesting question. This is what you are by default do. So all of you know. Now let me go to the second case. When the interest is to predict 0, how will my truth table look like? Or confusion matrix look like? What are my true positives now?
Zero will be true positive.
So this is true positive. This is true negative. Then what is my false positive? What is my false negative?
So
On
top
zero
right
is
will be
false
false negative,
False
negative,
negative, and this will be
false
false
positive.
positive. Is that right?
Yes.
Confident. Lock your jai for
Yes,
1 million.
yes.
Yeah, right. Okay. So this is right. So this is what you get. And the formulas remain the same. They do not change. This is always with respect to true positive, true negatives by total, true positive by true positive plus false negative, true positive by true positive plus false positive. These formulas never change. The values in the truth table, their interpretation changes, right? And this is where a lot of confusion starts to happen. When you are predicting zeros, when you are predicting ones, when your data has something, you fit a model for 1, and then if you are immediately asked to predict for 0, how do you compute your values? You just compute them by changing the confusion matrix. So that is why the confusion matrix is very important. Okay. Here is the question for you. You can develop this confusion matrix using logic all the time. It will always work. But in an exam or in an interview, when you are being asked questions, when you are under stress, how do you remember this table very easily? That is the trick that I would like to focus on for the remaining 10 minutes. Okay, right. And for this, all you have to remember is how to predict my true positives. If I'm able to get my true positives right, everything else will fall into place. Okay, right. So let me say my interest is to predict ones. Okay, and this is going to be my confusion matrix 0, 1, 0, 1, actual, predicted. So when my interest is predict 1, wherever 1, 1, I will put it as true positive. That is very clear. Once I've got this value in my matrix, all the other values I'll compute based on this. Okay. Then, if this is true positive, the diagonally opposite element is always true negative. Okay.
Right.
That is fixed. Next comes the interesting thing. Once you have got this true negative, for the next adjacent value, all you have to do is true negative. It's a true, so you put a false. It's a negative, you put a positive. So the opposite of the row value will come here. Same way, the opposite of this row value will come here. False, negative. So this would be your truth table. True negative, false negative, true false positive, true positive, true negative, false negative, false positive, true positive. Okay. So this is the most easiest way in which you can generate your truth table for any given data set. So tomorrow, even if your table is changed, let's say these are all sheets for you. Let's say it becomes 1010. Still, you will be able to generate the truth table by putting it as these are all my true positives, diagonally opposite true negatives. Once I get this, this will be opposite of this false, negative, so positive. So this will be opposite of this false, positive, so negative. So this will always match. Okay. This is how you generate a truth table, and all of this will be dependent on what you're trying to predict. If my prediction is 1, then my true positive location will be that. Now let's do the same thing for interest is to predict zeros. And let's say I give you this table. 1, 0, 1, 0, and let's change it a bit more. Yeah, let's put this actual predicted, right? So now what is my true positive?
Bottom right.
Bottom right. So after this, where do you go?
Diagonally opposite.
Diagonally opposite. So this will become a true negative. Once you have got these two values, true negative, so this will be
The 1, 0 will be false positive.
false, just opposite of this, positive. So 0, 1 would be just the opposite of this,
False
so
negative.
false, negative. Okay, that is your truth table. Okay, now comes how do you remember precision and recall? So
One more thing, sir, like
yeah,
if prediction and actual are changed, like axis, their axes are interchanged.
okay,
Can we try one example there?
okay, sure. 0, 1, 0, 1. You want this to be predicted, you want this to be actual. So 1 and 1 will be true positive. Diagonally opposite would be true negative. Since you have changed the columns, you should change it to rows now. It should be opposite. False positive and false negative.
Great. Yeah. This is very helpful.
Yeah, so this is a simple trick that you can use. Let's just check whether it matches. We are predicting zeros, right? So 1, 1 is true positive, 1, 0 is false positive, 1, 1, 0 is, one second. This is right, 1, 0. 1, 0 is false. No, you should not change. It should be same thing. False positive and false negative will not change.
So it will be changed.
One second. Let me just check it because I've never tried this. False negative, right? It should be the column. I've written it wrong. False positive. Correct. Yeah. The opposite of this would come here. The opposite of this will come here. False negative. Correct. Yeah. You're right. It'll change. I wrote it seeing this. That is why I got confused with it. It is true positive, so false negative. True negative, so false positive. Yeah. When you change the rows, you should also change the what you're looking at. When actual becomes there, you check the columns.
Right.
Okay. I've never done this. I've always stuck to this, but yeah. Okay. Now comes the very interesting part. How do you remember recall and precision? Okay. For both, the numerator is very simple. It's always true positive. So for all of these shortcut techniques, the numerator is always true positive. You always start with the true positive. Now, since it's recall, it is row, right? So when it is row, I will go to true positive and I will take the row. So it is going to be true positive plus false negative. And when it's P, precision, I will remember this as opposite of row, which is column. So I'll go to true positive and I'll take the column true positive by true positive plus false positive. This is the simplest way to remember your precision and recall formulas. Accuracy is always well known. So it is always going to be Tn plus Tp by the entire sample set. So that is no problem.
The way I remember it is like for precision, I take P for positive. So I add both positives.
Okay.
And obviously the recall will be the
recall will be the horizontal value. So that's what. So recall row R. So I just take the row.
perfect.
Precision P. Since it's opposite to this thing row, the next thing will be column. So it will take TP by TP plus CFP. That is all. Yeah, different techniques. It's just a way to remember. Yours also works. Precision is PP. So once I've got this, I'll take the row value. So there are different techniques to remember it. This is one easy way to remember.
Malalan, can I take 2-3 minutes for explaining precision recall without a confusion matrix?
Without a confusion matrix.
Yes.
Just tell them what precision means, what recall means.
Sure. Let me share my screen and give them. Malalan,
okay.
can you?
Okay, they have to make you host. Team, can you please make him host? Swaminathan as the host. Yeah, make co-host. You can now share. So you want to?
Malo, is the screen visible now?
Yeah, it is visible.
All right.
All of our names are there.
Yes.
Okay.
So let us say we are doing a search on the internet. We are doing this particular search with this keywords: co-instructor, IITM, BA, BDM, and the search engine is giving you 4 results, right? Dr. Malolan, Srivatsa, Mahesh, Kodai. So let's say these 3 are correct because these 3 are co-instructors and Kodai is an administrative person, and it is wrongly giving Kodai in this particular search. Apart from these, we have few more people who are instructors for the IITM, BA, BDM course. So we have Jaimini, myself, Ashwin, and Hariharan. So can we calculate precision and recall with this data? The answer is yes. You can even do this without a confusion matrix. If you look at the precision, let me delete this. If you look at the precision here, so there were 4 results the search engine returned, out of which 3 are correct. So the answer for precision here is 3 by 4, which is 0.75. On the other hand, if you want to calculate recall, so there are in total 8. There are 8 co-instructors for the BA and BDM courses, and out of which you got 3 correct. So it is 3 by 7. So
Swami, I think you just made an error. There are 7 co-instructors and 1 admin person. Yeah, so that is why 3 by 7. Yeah.
So there are 7 co-instructors in total, out of which you predicted 3 correctly, and therefore your recall is 3 by 7, which is 0.43. Right? This is another way to determine precision recall without a confusion matrix. This will give you a better intuitive understanding. Right? Any questions?
So the accuracy here would be 3 by 7, isn't it?
That's hold it. Maybe you can think about it, digest it a little more. It's a little tricky accuracy here.
Showed me the precision, I got confused with the accuracy.
So accuracy is little difficult here. So let us hold it for now. You can think about it and get back to us on this course.
Okay.
About the accuracy. So
think about it a bit more.
Yeah.
So if I take recall literally, that means how many items I am able to recall correctly, right?
So how many co-instructors are there in total, out of which how much you correctly predicted?
Yeah, so that is what recall is.
That is what recall is. Precision is from your predictions,
how many
are correct.
That is why you take the P, positives.
The accuracy is tricky because you don't have true negatives.
Yeah. Exactly. You got it, man.
So in the context of the regressor, how do we evaluate the performance using these parameters? Are we going to discuss that now, or?
We can. Okay, generally everyone is focused on accuracy, right? So precision is basically going to tell you amongst, how can I put this? Amongst all of your predictions, what is right? How much percentage is right? So that is going to be a prediction. So your accuracy will tell you the overall correct answers, whereas your precision and recall are specific to your class. So that is where you distinguish, right? So let's say you're measuring the side effect of a drug, whether a side effect is happening or not. Your accuracy might be very high, but let's say you're checking for whether there is a side effect. You want your precision also to be very high in that case, correct? So based on the context, you look at it. You'll not only focus on accuracy, you also focus on precision.
And
Exactly.
If you want both, sorry, please go ahead. Sorry.
Exactly. The context, how do we relate the context to these two parameters, right? For example, I think in one of the exams, there was this question, there is a metal detector and we want to be very strict about detecting, or we would want to be a little lenient about the detecting, because we do not want general public to suffer, or versus we at the same time we do not want the mischievous people to get away. So how do we interpret this general statement and relate to these measures?
So if you had learned about logistic regression, there's something called the threshold value, right? Which is basically going to classify it as 1 or 0. So by changing the threshold value, you can change your precision and recall for your problem. Correct? So if your focus is more on precision, then you will appropriately change the threshold value to be low or high. So that it will start to increase. After a certain point, it will start to drop. So you will go up to that point based on your requirement.
Right, that is a general understanding, but how can I relate it to these values?
That depends on your. No, you can relate it because your true positives change now. Your true positives and true negatives will start to change. Once these two changes, automatically the other two will change. Correct? So that threshold value, as you change that threshold value, your true positives and true negatives will start to change. And hence your precision and recall will start to change, and your accuracy will also change.
Okay, so do I have to change and then only I'll know, or with one?
Yes. No, you'll have to change it, and then, or else you have to do one more thing. Or else what you can do is, you can get the prediction probability. That will also be there in your tutorial video that we have done the Python code, or even in Sir's lecture. He will show you the predicted probability. You can use that predicted probability. Basically, the predicted probability, a threshold is put and you're changing, right? You can look at the predicted probability for your ones and identify a threshold. If your focus is on, you can, in this case, it's zeros. You can look at the prediction probability for your zeros and then identify a threshold such that your zeros are best predicted maximum. That can be done. You understand?
Yeah, I'm understanding, but I'm trying to understand the interplay between precision and recall. Like if I try to improve precision,
recall might change. In most cases, it will change.
So will it reduce or increase? We
yes.
don't know, sir.
No. Yeah, this value reduce or increase will depend on your scenario, because what is recall? It's false negatives now. So if you are increasing your false positives and this number is shifting here, then this will remain the same. But what if this number is shifting there? Or some numbers from here are shifting here. That depends on the scenario to scenario, right? It is just a movement of numbers, the count, not numbers, the count. And when the count moves in a particular direction, automatically your recall will change. In which direction it's moving depends on your problem.
So let me give you two applications or two scenarios where precision and recall is important. For example, let us take a task of predicting whether a patient is having cancer or not. So here what you will reduce, whether you will reduce false negative or false positive, which should be given more importance here. The answer is false negative. You will try to reduce the false negatives here. On the other hand, let us say that you want to, you are working on a logistic regression tool that is going to detect whether your email is spam or not. So here, your objective will be to reduce the number of false positives. So both are two different scenarios. So in one, precision is important. In the other one, recall is important. So if recall is important, you will have cases where you will reduce false negatives. Similarly, if precision is more important, you will reduce false positives and so on. It depends on the context, as Malalan said.
And the values for these, the count for these will depend on your threshold. And your threshold will get affected by your prediction probability, which is given by your model.
So if you want both to be, if you think both are important, precision as well as recall, use another metric called F1 score, which we have not covered in this particular course.
Got it.
I think it's too much. We are deviating from the business analytics course. So I think it's a good point to stop here.
Yeah, but I hope you understood what we are trying to say. Yeah.
Yes. Thank you.
All right. Yeah. So we have hit the time. Any questions? I see chat messages. I didn't see this. So that all collab codes are, yes, all collab codes are available in your drive. Did you check for me? It is a left tail. Negative skew. Okay, I will get back to you on this. I have to check the formula for skewness. Negative skew is left tail. Check it right now. Left skewed because it is x minus x bar. Okay. X minus x bar. So it is left skewed. Negative skew is left skewed. Yeah. Someone was asking me what does negative skewness mean? Negative skewness means left tail because it is x minus x bar. Value minus the mean value. All right. Anything else? All good. Okay. So if there's nothing else, we can wind up the call. Thanks for joining. Have a look at the week 7. And in case if you have any questions on week 7, please feel free to tag us in the discourse and we'll be happy to answer. Yeah.
Thank you so much for the session. Thank you so much.
Thank you, Malalan. Thank you all.
Thank you.
Thank you. Bye-bye.